Chapter 7.2 Trigonometric Integrals. In this section, we use trigonometric identities to integrate certain combinations of trigonometric functions. We start with powers of sine and cosine. Example 1, evaluate the integral of cosine cubed x dx. Solution: simply substituting u equals cosine x isn't helpful, since then du equals negative sine x dx. In order to integrate powers of cosine, we would need an extra sine x factor. Similarly, a power of sine would require an extra cosine x factor. Thus, here we can separate one cosine factor and convert the remaining cosine squared x factor to an expression involving sine using the identity sine squared x plus cosine squared x equals 1. So cosine cubed x equals cosine squared x times cosine x equals open 1 minus sine squared x close cosine x. We can then evaluate the integral by substituting u equals sine x, so du equals cosine x dx, and the integral of cosine cubed x dx equals the integral of cosine squared x times cosine x dx equals the integral open 1 minus sine squared x close cosine x dx equals the integral of open 1 minus u squared close du equals u minus 1/3 u cubed plus big C equals sine x minus 1/3 sine cubed x plus big C. In general, we try to write an integrand involving powers of sine and cosine in a form where we have only one sine factor and the remainder of the expression in terms of cosine, or only one cosine factor and the remainder of the expression in terms of sine. The identity sine squared x plus cosine squared x equals 1 enables us to convert back and forth between even powers of sine and cosine. Example 2. Find the integral of sine to the 5th power x cosine squared x dx. Solution: we could convert cosine squared x to 1 minus sine squared x, but we would be left with an expression in terms of sine x with no extra cosine x factor. Instead, we separate a single sine factor and rewrite the remaining sine to the 4th power x factor in terms of cosine x. Sine to the 5th power x cosine squared x equals open sine squared x close squared cosine squared x sine x equals open 1 minus cosine x close squared cosine squared x sine x. Substituting u equals cosine x, we have du equals negative sine x dx, and so the integral of sine to the 5th power x cosine squared x dx equals the integral of open sine squared x close squared cosine squared x sine x dx equals the integral of open 1 minus cosine squared x close squared cosine squared x sine x dx equals the integral of open 1 minus u squared close squared u squared open negative du close equals negative integral of open u squared minus u to minus the integral of open u squared minus 2u to the fourth power plus u to the sixth power close du equals negative open u cubed over 3 minus 2u to the fifth power over 5 plus u to the seventh power over 7 close plus big C equals negative 1/3 cosine cubed x plus 2 over 5 cosine to the fifth power x minus 1 over 7 cosine to the seventh power x plus big C. Sidebar, figure 1 shows the graphs of the integrand and sine to the fifth power x cosine squared x in example 2 and its indefinite integral with big C equals 0. Which is which? See figure 1. Back to the text. In the preceding examples, an odd power of sine or cosine enable us to separate a single factor and convert the remaining even power. If the integrand contains even powers of both sine and cosine, this strategy fails. In this case, we can take advantage of the following half-angle identities. See equations 17b and 17a in Appendix D. Sine squared x equals 1/2 open 1 minus cosine 2x close, and cosine squared x equals 1/2 open 1 plus cosine 2x close. Example 3. Evaluate the integral from 0 to pi of sine squared x dx. Sidebar, example 3 shows that the area of the region shown in figure 2 is pi over 2. See figure 2, y equals sine squared of x. Back to the text solution. If we write sine squared x equals 1 minus cosine squared x, the integral is no simpler to evaluate. Using the half-angle formula for sine squared x, however, we have the integral from 0 to pi sine squared x dx equals 1/2 the integral of 0 to pi of open 1 minus cosine 2x close dx equals open bracket 1/2 open x minus 1/2 sine 2x close bracket on the interval from 0 to pi equals 1/2 open pi minus 1/2 sine 2 pi close equals 1/2 open 0 minus 1/2 sine 0 close equals 1/2 pi. Notice that we mentally made the substitution u equals 2x when integrating cosine 2x. Another method for evaluating this integral was given in exercise 7.1.47.